In the last video, we looked at what makes a function continuous. And if the function is not continuous at this point, which means that it doesn't satisfy one of these three conditions, then we say the function is discontinuous at that point or not continuous at that point. Or we might say that it has a discontinuity at that point. So in this video, we want to explore this concept of discontinuity. Specifically, we want to look at the different types of discontinuities. So we can generally classify these into three different types. So on the graph here, I have three different functions which are all discontinuous at 0 specifically. Okay, and they're all overlaid here. So the purple line, you can see this is the function, the absolute value of x divided by x. The white line is the function 1 divided by x, and the red line is the function x squared divided by x. So clearly these are all discontinuous at 0, and if it's not clear, you can show that they all, really they all fail the first condition, right? That they're all undefined at 0. So that's preventing them from being continuous. But it's also clear that they all look different, right? They all kind of look different at 0. So these are all examples of a different type of discontinuity. So let's look at them all individually here. Let's just look at the red one first, the x squared divided by x. So here it's continuous except at this 1.0, and then it just keeps going along that same continuous line. So it's like this little tiny blip on the radar, right? This is what we call a removable discontinuity. Removable as in, we could just remove this one little spot and then it would be continuous. Okay, and I'll write all of these down, of course. Just want to kind of explore these first. This one right here, 1 over x, this one's a bit different. It's not something that we could really think about removing, right? Because even if we remove the discontinuity at 0, there's no way for these two sides of the function to connect together, right? So this is what we call a infinite discontinuity, meaning that the limit is going to infinity. And then the last one is the absolute value of x divided by x. This one, it kind of has a similar issue, which is that even if we were able to remove that discontinuity somehow, it still is going on completely different paths around that discontinuity, right? So to the right of it, it's going down the line 1, and to the left of it, it's going down the line -1. So there's more of a problem than just that one little point. There's also the fact that there's a jump between the points. So we call this a jump discontinuity. Okay. So let's go ahead and define all of these and look at how can we tell which is which without necessarily having the graph. Okay. So if f of x is discontinuous at a, I said in the last video that the word discontinuous sounded kind of funny to me, but I guess that was just me. I see that word being used all over the place. So if f of x is discontinuous at a, then if f has a removable discontinuity. Okay, so removable discontinuity at a if the limit as x approaches a of f of x exists. Okay. And remember that this means it has to be a real number, not infinite. So this would be, like we saw on the graph. Again, if we go back to the x squared over x part and we see the discontinuity at 0, the limit as x approaches 0 does exist, right? It is 0. So this is why it's classified as a removable discontinuity. Okay, so the second type, f has a jump discontinuity. At a if both the limit as x approaches a from the left of f of x and the limit as x approaches a from the right of f of x exist, but are not equal. Okay, so the limit overall does not exist, but the both of the one-sided limits do exist, right? So this would be a jump discontinuity. So again, this is like the absolute value function divided by absolute value of x divided by x. We'll just go back and forth here, right? So here the limit as x approaches 0 from the left is -1. The limit as x approaches 0 from the right is +1. So the limit overall does not exist, but both one-sided limits do exist. And then finally, infinite discontinuity. That one's probably rather easy to guess, right? F has an infinite discontinuity at a if the limit as x approaches a from the left of f of x equals plus or minus infinity, and or the limit as x approaches a from the right of f of x equals plus or minus infinity. Okay, so it just needs to be infinite on one side, right? And it could be infinity on one side, it could be negative infinity on one side. We're just some kind of infinite. It doesn't matter what the sign is. Okay, so let's look at a few examples of how we can classify a function's discontinuity without necessarily relying on the graph, just by looking at the math. Okay, so you'll kind of get used to this, hopefully, with practice, and be able to recognize different functions and exactly what kind of discontinuity they have, because usually you can tell just by the type of function that you have. So x squared minus 4 divided by x minus 2. So at 2, this function is going to be discontinuous because f of 2 is undefined, right? But notice that if we do a little algebra here, this is x minus 2 times x plus 2 on the top, x minus 2 on the bottom. So these do cancel out and we get x plus 2. So when we take the limit as x approaches 2 of f of x, we just get 4, right? For the left and the right sided limit. So the limit overall does exist. So this falls into the first category then. So this is going to be a removable discontinuity. Okay. Rather than rewrite it, let's go back up to one that we already did in the last video, this one right here. So we showed that this is not continuous, right? So let's try to classify this discontinuity now. The limits on both sides do exist, but they are not the same, right? So the limit overall does not exist. So this means that this is a jump discontinuity. All right, so let me just write it right in here. Jump discontinuity. Okay. Okay. Let's look at one more here. Okay, let's consider the function f of x equals 1 over x squared. Okay, which I feel like we looked at, but it's going to be similar to 1 over x, of course, right? So the function is not defined at 0. The limit as x approaches 0 of f of x is equal to infinity. And when we say the limit is equal to infinity, this means that it agrees on both sides, right? It's going to be the left side limit is going to be infinity and the right side limit is going to be positive infinity, both going to the same infinity. So we'd write that it's equal to infinity, which means it does not exist, but this is going to be an infinite discontinuity, right? So basically this will happen when you approach the vertical asymptotes, right? So if we look at a different type of function now, one that we haven't seen, like the logarithm function, for example. So the natural log of x. At 0, this function is clearly not continuous because f of 0 is undefined. But what kind of discontinuity would this be, right? So it's a little bit tricky here because we can't even really talk about the limit from the left side because this function is not defined to the left side of 0. But we can still talk about the limit from the right side, right? So the limit from the right side of f of x is equal to negative infinity, okay? And this should be clear from the graph. Okay, the graph of the function looks like this, where this is the point 1, 0. And it has a vertical asymptote at x equals 0. So you can try this out with a table. Like if you keep putting in smaller and smaller values of x, like 0.01, 0.001, you'll see that it's going towards negative infinity. So the limit as x approaches 0 from the right is negative infinity. And if we note from our definition, we need f to have an infinite discontinuity a if the limit as x approaches a from the right is positive or negative infinity and or the same thing on the left. So we only needed to satisfy this on one side. So we would still call this an infinite discontinuity. Oops. Okay, so then just to kind of look at other functions that we haven't really touched on in the continuous section here. Functions like e to the x or any of the exponential functions, these are continuous everywhere. Okay. So again, hopefully that's clear from the graph. It does have a horizontal asymptote, but there's no vertical asymptotes and there's no jumps or removable discontinuities. Okay. The functions sine and cosine are continuous, right? Continuous everywhere. I'll just write continuous here. Again, hopefully clear from looking at the graph, right, where they just oscillate. Tangent is not continuous everywhere, right? F of x equals the tangent of x. This has infinite discontinuities. At pi over 2, 3 pi over 2, negative pi over 2, right? So we would write pi over 2 plus k pi, where k is an integer. The way we write the integers is sometimes with this fancy z symbol. So it could be 1, 2, 3, -1, -2, -3. Okay. Something like the cube root of x is continuous. Okay. And if you just go back and look at the video on, or the notes on, all of the special types of functions that we looked at, hopefully most of these will be clear from the graph. The standard absolute value of x, so we looked at absolute value of something divided by something, but just the regular absolute value is continuous. Okay. One of the ones that's kind of tricky would be the square root function. Okay. Okay, so the square root function. So let's think about this one for a minute on its own. Okay, so this is what this function looks like. So we have the point, it is defined at x equals 0, right? And then it kind of looks like this. Now, I do want to say, I don't know if I'll have a separate video on this, but we do have this notion of right continuity and left continuity, which is that we say something is right continuous if the limit as x approaches a from the right of f of x equals f of a. Okay. And then similarly for left continuous, if the limit as x approaches a from the left of f of x equals f of a. And we can say a function is continuous at a if it is both right continuous and left continuous. Okay. So we do have this notion of right and left continuity. So I think it's clear that this function is at least right continuous. Okay. F of 0, and we're only looking at the point at 0. F of 0 is 0. And the limit as x approaches 0 from the right of f of x is also clearly 0, right? That's where it's going. The question is, what is the limit as x approaches 0 from the left, right? It's an interesting question because it's not defined to the left. And our definition of a limit requires it to be defined immediately to the left. So we can't really talk about the limit as x approaches 0 from the left. We can't even really say that it doesn't exist. It's more like it's not even defined at all, right? Because there are no points to the left of 0. So if you look at different sources, you'll find kind of different answers about this. In the textbook, the Stewart textbook for calculus that's frequently used, they don't necessarily touch on this specific case, but I do think it's kind of clear that they imply that this would be right continuous, but not necessarily continuous overall. Some sources will only consider continuity on the domain of the function itself, which means that they're not even really looking at infinite discontinuities, right? Because those occur at points outside of the domain. But this function, we could say that it is continuous on 0 to infinity, 0 included. So, and this is the function's domain as well. So we would say the function is continuous on its entire domain, just like we do for, the rational functions and the polynomial functions. But this is really only if you are saying that, it doesn't make sense to talk about the left-sided limit because there are no points over there. So it's really a matter of convention, and you're not going to find one solid answer on this. It's maybe there is a more precise definition of continuity, just like there is for limits, where you use the epsilon and deltas, and you can maybe get a better answer out of that. But most sources I've seen will say that this is continuous on 0 to infinity. Some will say on 0 to infinity, not including 0, because again, you're not technically getting the left-sided limit at 0, so you can't technically get the continuity there. But if we just use like a more simple definition of continuity, as in like, you can draw it without lifting your pen, it does fit that definition of continuity, right? So I feel like intuitively, it's natural to consider this continuous at 0. But on a more technical level, I would say that it's only right continuous. Okay, so this is just one of those special cases. Most of them will fall into one of the more clear-cut cases right here. It's really only special because it gets cut off so suddenly here.